So thank you for coming to this grab bag. I did start to think, I thought, right, I want to contribute something, but wasn't entirely sure what to contribute. So I went back sort of 8 years ago and thought, right, I'll pick out something I did in my dissertation. So I have been looking back over my old notes over the last sort of like couple of weeks, and it's been quite interesting that a lot of the stuff that I struggled with second time round is the maths. So I thought, right, I'll try and contribute in such a way that kind of ignores the maths and concentrates on the theory and the practicality behind it, rather than going too deep into solving quadratic programming problems and that sort of thing. Who here has actually heard of a support vector machine prior to this brown bag? I thought you might have done. Basically, you're all familiar with neural nets? Perceptron? Yeah.
No. Perceptron.
Perceptron, yeah, a single neuron. That's sort of like, I'll explain a little bit about it in a minute. But essentially, support vector machines are considered kind of like a form of neural network. So I'm going to sort of give you some background on what they are, and kind of explain how you actually apply the theories behind it into, solving problems like data classification. So a bit of background: it's not fairly new technology. It's going back to 1992, so 20 odd years, and it's something that's gained a lot of success in the field, sort of like around handwriting recognition, and it's still relevant today. So it's quite an interesting sort of subject to pick up on and learn a bit about. Uses supervised learning techniques. Now, to explain a little bit about that, you have supervised and unsupervised learning. It's kind of a little bit self-explanatory. Supervised learning it implies you know a little bit about what the problem you're trying to solve up front, so that you can then make decisions on finding an optimal solution. So you kind of give the network a training set, and then you make decisions because you know what that training set is. Say for example you have like some training data which was the list of sort of pictures of cats and then a list of pictures of dogs. You take that training set and you go, right, I know these are dogs, so I'll feed them through. What I get out the other side, is it a dog, is it a cat? Is that right or wrong? Feed it back in, and you make a decision on updating the network based on the data that you know. So unsupervised learning are kind of like, you don't know anything about it, and therefore it's kind of like you're evolving as you go along. So support vector machines are really used for data classification and data analysis. I'm going to use sort of data classification today as a way of explaining it. So just imagine you have like that scenario of dogs and cats, pictures of dogs, pictures of cats. You feed it into a support vector machine, and the idea of a support vector machine is to tell you that is a cat, that is not a cat, or that is a dog, that is not a dog. Is that all clear so far? Cool. Well, so to start with, if I talk a little bit about neural nets and the starting of neural nets of the perceptron, the idea behind neural nets really is to kind of artificially simulate the biology of the brain. So the idea that you have connections going into neurons, and then once that neuron reaches a certain threshold, it then fires off another connection, which will then connect up to several other neurons. So the idea being is that you have your input layer, so you'll have sort of like your inputs firing in here. That could be artificially, it could be anything from like a 0 to 1. It can be mapped however you want to map it. They come in, and then you have a weighting on each connection. So in your brain, some connections are strong, some connections are weak. So these weights kind of symbolise that. And then when all of those weights going in, when that hits a certain threshold, it then fires off a spike. And in sort of like computer science terms, we can use a sigmoid function, which is to take a value from 0 to 1, and if it's above 0.5, you make it 1. If it's below 0.5, you make it 0. So it just turns like kind of like a decimal value into a binary value, really. So the idea behind support vector machines is to take this perception idea and kind of grow on it and identify the areas that it fell down and try and improve on that and try and make it actually solve those problems, which I'll go into in a little bit. One thing to note though, that the perceptron really, it's reliant on the data that you give it being linearly separable, and that will all become clear in a minute.
Ian,
yeah.
Are the inputs and the outputs up there are always binary?
From here, yeah, so you can be, it's up to you, you can either make them binary or you can make them non-binary. So classification wise, really you kind of want to make them binary. So say for example, it's, say you were like solving like an AND or OR problem, you give it zeros and ones.
Yeah.
So you give an input of 0 and an input of 1, and then you'd expect, depending on what you're trying to solve, whether it to be a 0 or 1 coming out the other side. So I find it easy to kind of explain the perceptron in form of binary values, really, because it's easy to explain its downfall when you're trying to solve problems like the XOR problem, which is non-linearly separable.
Well, in general, they don't have to be binary. Inputs, they can be real values as well. Usually there is also a problem of normalization, so they should have the same magnitude,
Yeah.
this to make sense. And output, if it's classification problem, you want it to be binary.
Yeah.
But you can have regression problem, then you want number.
That's right. Essentially, you can kind of consider this as being a function. So you, kind of like a black box, you give it some values to input, it applies a function to those values and generates your output. So, okay, so when I talk about input space, you've got your input layers. So if you consider it as two inputs, it gives you kind of a 2D representation of your input space. So say if it was something you were feeding in like a value from 0 to 1 for height, a value from 0 to 1 for depth on something, say if you're trying to determine shapes. So you've got your x-axis, your y-axis, and the idea being, when I talk about linearly separable data, when you plot the data that you're given, say you're trying to identify what's a circle and what's a square, they are, as you can see, linearly separable. You can draw a line anywhere in there in order to separate your data, and that's the idea of classifying the data. You find that function that separates those two forms of data, and that gives you your decision, and that gives you a solution. Does that make sense so far? So the problem of data classification, as it's just explained, is actually trying to separate that data. So it is finding a decision boundary which satisfies the conditions that you know, which is I can take all of these that I know about, solve the problem, draw a line between them, and then from that point forward, any new shapes that come in, say something down here, you can classify that that's going to be a blue square as opposed to a red circle. Now obviously that's not for definite because you're only going on the data that you've been given and fed in, and that's half the problem of trying to build neural networks and support vector machines, is trying to build one which actually gives you the best sort of like best generalization. And generalization is actually feeding in data into the network that you haven't seen before. So you may have trained this perceptron to give you that kind of decision boundary, but you then want to, and that's based on all these values that you know about, but then you feed in a new one, which may be somewhere like here, and it's about building a perceptron that can actually, and optimizing so that it can actually solve those sorts of problems where you feed in new data. So say you had 10 pictures of cats, 10 pictures of dogs, you train up your neural network to distinguish between those two. Then you come in with a brand new picture of a dog, say with a different background, what have you. The neural network is kind of judged on how well it can actually classify that data based on data it's not seen before. So you have your training, which is this, And then you have your generalization, which is feeding it in new data. So, decision boundaries. As a perceptron, you're just going to try and find a line that separates that data, but which one should you choose? Which one is the best? All of these lines here satisfy the condition that you're trying to set, which is separate the red circles from the blue squares. But which one would be a good fit for throwing new data? So, say if I had a new red circle that was here, you can see that these lines here satisfy the condition, but these two don't. However, they do satisfy the condition of the training. So half the fun in building these neural nets and building support vector machines is trying to optimize them in such a way that when you feed this new data, you get the best sort of like results. So in order to decide what's a good decision boundary and what's a bad decision boundary, as you can see here, it may be obvious to begin with that that might not necessarily be a good decision boundary. In the case that, what about this sort of like area here? We don't know in terms of new data coming in whether or not there's going to be red circles here, or whether this is all just going to be blue. So generally, a good way to think about a good decision boundary is a boundary that actually separates itself as far as possible from each data set. Now, support vector machines, the idea, one part of them was to take...
Isn't that making some serious assumptions about your training data, though, that the mean, if you like, is going to be the best?
That's right.
Because they might be skewed.
They might well be skewed, yes. And that is the problem really with trying to build a network.
Well, with insufficient data.
Yeah. So generally, obviously, the more data you have, you can kind of train it up to...
As long as it's not all skewed.
However, yeah, the trouble is that you can often find that you can overfit the neural network to suit the data. Say, for example, all of your pictures of dogs happen to be with background of grass, so a nice green background. Then, and all your pictures of cats happen to be sort of on sand, for example, for whatever reason. I don't know why you put your cats on sand, but then you take a picture of a dog on sand. It's how well it... you might find that you've over-fitted your neural network to suit the generalization on things like the background rather than the actual object you're trying to match. So it's quite an interesting problem to solve. So support vector machines, one of the main key areas that they try to solve is actually this problem. And it does make an assumption that actually with the data that you have, ideally the best possible solution to finding a decision boundary is finding one that is as far away from each of the data classes you were trying to separate. So as you can see from here, you find your two decision boundaries, and this is the furthest away between these two. So they call it a large margin decision boundary for that reason. You're trying to basically solve... You've got two things you're trying to solve here. You're trying to solve the actual condition that everything that side is a blue square and everything that side is a red circle. But you're also trying to solve the problem that I want to maximise the margin between each data set. So there's two sides to this optimisation problem. Now with perceptron, the optimisation problem generally is just to find the solution. Support vector machine will take that a little bit further and try to find a more optimal solution. So this is essentially what that's trying to do. So it's a constrained optimization problem, and it's what you call a quadratic programming problem. I tried to avoid the maths as much as possible, so I thought I'd at least show you exactly a little bit about what it is it's trying to do there. Now, the reason why I've tried to steer clear of the maths is because there's all kinds of tools out there now that solve it for you, and there's all kinds of libraries out there that do it for you. So a lot of what I'm going to talk about here has already been done, and it's a black box. So if you do fancy having a little go at programming something, either get your head into the maths behind it and have a look, go at actually solving the quadratic programming problem, or have a look at some of the libraries and use the tools that are already there. So that's why I thought I'll ignore the maths today. Partly because also it's going back over it again after 8 years. A lot of it I don't understand anymore either. So but that's essentially what you're trying to solve, and that's the optimization problem of trying to find the optimal decision boundary between your two data sets. So support vectors, the reason why they're called support vector machines, essentially is in finding this, realistically, once you've made that decision that you're trying to find the maximum margin between the two data sets, realistically, you're only really looking at what we call here support vectors, which are the training points which are so reliant on they're so important that if you were to move them, it would change the whole scope of your decision boundary. So if you were to remove this one here, the chances are it's going to be more biased towards here than it is towards here, if that makes sense. So if you move them, it will completely change the scope. If you were to move these, it wouldn't make any difference. That is still the most optimal solution. If you move,
so in your diagram there, you've got two boundaries as being parallel.
Yeah.
Do they have to be, or are they just whatever that fits the data?
if you're trying to find this green line is essentially what you're trying to find, and that green line has to have the maximal margin between itself and the data set you're trying to classify on both sides. So realistically, you are looking at, like these three lines are always in parallel. So you split the two data as best you can using two lines, if you like, conceptually, and then that middle line is your optimal decision boundary.
I don't see why they had to be parallel, because if they weren't parallel, you could draw the triangle and bisect it, and that would be your green line.
You could, but that's like going back to perceptron. So imagine you've got two inputs and you've got one output. Say in this example, you've got a value for x and you've got a value for y, and you get a 0 or 1, a binary value out of it. That 0 or 1 tells you whether it's a circle or a square. So the idea of trying to find a function that solves that using two inputs, one output, it's essentially can be considered as a straight line. So if you were trying
but the two lines don't have to be parallel, do they? The red and the blue?
If you're trying to solve the problem that you want the maximal margin between your decision, so your green line, and the two data sets, this is just a way of finding that.
So because if they weren't parallel, then they would intersect, and then you get ambiguity after they intersect.
Exactly. So if they were to, if you had that kind of setup, and you want this another colour as well. So this is essentially what I've drawn. The green there and that. If you were to use these two here, which yes, they best fit that data, it's finding the most optimal. I guess you could find that as being the most optimal, but that doesn't solve the condition of, well, I want to maximise the margin between each decision boundary.
It can maximise it.
It does maximise it in terms of the theory, yes, but if you're trying to solve it as a linear function,
it doesn't actually massively intersect, because it's not those lines that you're using, it's the lines that you're using. So I still think you could have.
No, this is a specification of the actual classifier as a separate vector machine, that actually you look for those boundaries. But you have to remember that this is like a simple case, the same as one neuron case. It's very simple case like that. It just finds the hyperplane, if you want to say, because normally you never have 2 dimensions, you have 100 dimensions. Hyperplane that separates, and the same with support vector machine, you just find the better hyperplane that just satisfies these constraints. If you want to classify some more complicated structures in your space, so you want to have like triangles or curves, then you use combination of support vector machines or like perceptrons as well. You form network of them to perform more complicated classification.
But aren't your lines decided by the positions of elements within your set? You're not guaranteed that you're going to get two lines that are, I mean, or are they? Are your lines decided by 2 elements within each category?
Yeah, they're gonna be, in this case, they're gonna be decided by 2 elements, yeah.
But
Just to
you're not guaranteed that that you have 2 elements, the 2 closest elements to the opposing set are going to form parallel lines.
So just to reiterate on what Carl said, if you take the simple scenario of a perceptron, it just has 2 inputs, it has 1 function applied inside it, and that gives you 1 output. That's good for solving like linear separable data because it draws it's a straight line. It draws a straight line through your input space. To solve more complex problems that are non-linearly separable, you'd build a more complicated structure of several neurons. You'd have your 2 inputs, then those would have weightings going to a hidden layer of inputs, and then those would then make decisions based on other values. Each one of these has a weighting, so you end up with more connections, which gives you more complex sort of scenarios to solve. So if you imagine a perceptron, really, all it can really do is it can basically effectively draw a hyperplane through your input space. So it just draws 1 line. So with that, it will go through and try and find lots of different ways, well, lots of different lines essentially for your input space to find the right one that actually separates your data. This technique here is a way of finding a line which is more likely to solve new cases. So say for example you've got a blue square here. With just any old line going through, you can't really kind of guarantee that it's going to perform well. But one thing you do know about your data, even though you have only got this data here and this data here, you know that actually I'm going to find a trend that best fits this data. And the way that you find the one that best fits is the way that you actually maximise the distance between that best fit, the decision boundary, and each of the classes of data you're trying to separate. Does that make sense?
So we're saying that
Your point was right, that they're not necessarily going to be parallel.
If you get rid of that bottom,
But you can have 1 support
point.
vector. You don't have to have 2, you can have 1.
Yeah.
But does that imply that
so
the
it doesn't
argument-
necessarily have to be, maybe that picture is a bit
Try not
misleading in
to-
a sense, but that's a fair point.
Yeah, try not to think of this technique as being the optimal, like this is it, this is the only way you can do it. Yes, if you could think about this theoretically and have 2 lines that weren't parallel, and then form a decision boundary based on that, maybe there's some maths in there that you might be able to find it. But if you take the theory that actually all I know about this data is that there is a general trend, and that what I want to find the most optimal decision in that trend that is more likely to going to give me better accuracy when I feed it new information. So it's
so
kind
you're
of
saying that basically if the problem did have that kind of representation, then this argument will work. But if the data was skewed so that there were no 2 parallel lines, then it just wouldn't work as well.
Yeah, I mean, it will work for your training data, but if you then find that actually, based on that training data, it is linearly separable. But you might find when you feed it new data that actually the real problem is non-linearly separable, in which case you need to readjust your network and make it, which I'll go into in a minute about actually making it work for non-linearly separable data.
So if that's that case, you probably get some kind of curve rather than a line.
That's right, yeah. Yeah, so you can imagine that
You can have spots all over the place.
You can, yeah.
Red and blue.
In fact, I'll demonstrate that. I mean, I've got some diagrams for that rather than trying to draw it. But does that make sense? So try not to think of it as being that is the. It's just a theory on what you know about the data so far, and a way of actually trying to make the perceptron better. Because if you just take a standard perceptron and you're just trying to solve a problem and you're with separating the data, you could end up with a bad decision boundary, which isn't very good for feeding new data in.
So you're kind of taking two lines, shoving them in the gap, squeezing them apart
As far as
they can, and parallel until they hit a point.
That's right. And then your
They may not hit
decision
2 points,
boundary
they may only
is
hit 8
parallel
points.
to that in the middle, because that's as good as you're going to get, really, knowing what you do about that data and that trend.
Because you've got 2 points for each color, and really it's only 1 point you're looking for, because it's the first element it hits that you have to stop at.
So
Because if, for example, if you got rid of that bottom blue point,
this one here, yeah.
right, then you'd be adjusting, you'd have to.
That would adjust the parallel lines, yes.
Well, it wouldn't adjust the lower. You wouldn't be able to change the lower one because the closest red and the closest red points are already there. Any adjustments on the red one.
Say, for example, you remove those two. Say, for example, that one didn't exist from the start.
Okay.
That's your line of best fit. If you remove that, suddenly the line could be more susceptible to doing something like that.
But I'm thinking if you just remove the blue, the lower blue one.
That's right. Yeah, I'm saying if you remove the lower blue one, but forget about that one.
Then you're getting rid of 2 points.
Yeah,
So
I drew this diagram about midnight last night.
Okay.
So yeah, bear with me. But if you forget about that one and what Mike's saying, if you then take away that one, yes, that alters your decision boundary completely, because the data shifts more. The trend shifts more to something like that than it does more of a sharper line. So, with that being said, that's why support vectors are support vectors, because you take away one particular piece of training data, which is a support vector, that can completely change your decision boundary. So they are very susceptible to the data that you train them on. Does that make sense so far? It's like I say, try not to think of it as this is, because half the problem with neural networks is they have error rates. They're not going to be able to. You're not going to be able to give a picture of a dog and a cat in every situation in the world, and it magically tell you yes, that is a cat, yes, that is a dog, because you can only train it up based on what you give it. And the optimization problem, thinking of a zero non-zero curve, you'll decrease the error that you have over time. The more you train it, the more you feed it in new data, but you'll never actually get it absolutely perfect, because if you think like even humans aren't perfect. So, does that make sense?
No, humans aren't perfect.
Some of us are, some of us aren't. So yeah, like I said, try not to think of this as being this is like the scientific proof. This is the best way to do it. It's a theory, and it's taking what you know about your input space and trying to make something more optimal.
But you always need 2 points for a support vector then?
Ideally, you need at least a minimum of 2, because you've got to separate the two classes.
In support vector, you define everything that lies on this hyperplane. That's support vector. So I don't know, maybe they can be 3 or 4.
At least
Yeah, they can be as many as.
I'm not sure, but can we have 1?
I don't know if you can have 1. If you think
That's
about
what
it,
I was thinking about.
if for the classification problem you're trying to separate 2 data sets, you're going to need at least 2.
At least the combination. Okay.
Don't you mean like 1 on one side?
Yeah, I mean like 1 on 1.
Yeah, so 2 in
Oh,
total,
so-
but
yeah, 2.
1 of each type.
Yeah.
That's definitely proven. This
Yeah.
whole thing is, I think, 90 several properties.
So, getting on to that discussion around non-linearly separable data. So, say for example here, you can't draw a straight line through this. Same with the XOR problem. It's something that cannot be solved by perception because it can't be considered as a straightforward function with 2 inputs, 1 output, 1 function. It can't be done. So from that point, that's why we went from perceptron and started building these input layers in the neural network to give you more complicated functionality so you can actually separate that data. And instead of it separating it with a straight line, it's a curved line if you're considering it in this input space here. Does that make sense? So it could be a curved line, or you should find out that actually this line goes here like this in order to separate the blue from the red. And the only way you can get that is by a more complicated network structure rather than a simple perceptron.
So visually, if you just added, say, 1 or 2 input layers, does that just add extra lines to the...
It gives you, yeah, it gives you more of a dimensionality to working. It gives you extra lines.
But you wouldn't get a curve unless you had like an infinite number of layers.
No, it's kind of like an average.
3 layers. 3 layers.
Three
You can have
layers.
any convex
Oh, okay.
It's
separation.
like kind of averaging because it's all weighted.
Right, right,
So,
right.
Yeah. So each layer, so you have your input here might be, let's think of it as binary input, so you might have the 0 and 1. Each one of these connections has like a weighting. So you have like a weighting of, I don't know, it might be 0, a value from 0 to 1, that might be 0.8, which would consider this input to be more important than that, given a certain decision. But then, because you've got this layer here, that might be 1.5, that might be 0.8. And this might be, say, 0.2, this might be 0.9. And it's the same going forward. So you feed in a 1, and each one of these as well has like a bias value. So that might be, say, 0.8. And you define your function by the product of your input by 1.8 plus the bias. That then fires that value up to here, that has a weighting there, and it sort of like feeds through the network. So
Or is it the training that actually sets the weights on there?
that's right, your training is when you, so the idea behind trying to train a neural network is you know you've got a picture of a cat coming in here, and you're trying to classify 1 as being a cat, 0 as not being a cat. So based on values, this might be, say, I don't know, height, width, I don't know, whatever you want to call each of these input values. So you feed that data in, what comes out the other side may be 0, so that's incorrect. So what you do, you go back and you think, well, okay, how far was I away? And you adjust these values in a certain direction to see if that makes you any closer to the right decision.
You have a learning coefficient for that.
That's right, yeah. So you kind of train over time, over epochs, you kind of train up that network to suit the data that you're giving it and the answers you're expecting back.
So it's like heavy and low
Yeah.
feedback.
Yeah, I mean, there's heavy and low. Traditionally, I think the most popular one from neural network is what they call back propagation, where you kind of, you know about what it is you're expecting, you adjust back. And slowly but surely over the amount of pictures of cats that you show it, eventually it will start making sort of decisions based on the input you give it and your training algorithm. So as slowly over time it starts to recognise trends and think, hold on a minute, yeah, this is a cat, this is a cat, this is a cat. So, but as I said earlier, the temptation is to really feed loads of information in and loads of training data to help your network kind of spot cats. But the trouble is that you can overfit that data. So it's so kind of tuned to the training data that you give it, that when you give it new data, it's not free enough to kind of make.
It goes, this isn't a cat I've seen before.
Yes. So that's what you call overfitting.
So you can need 3 layers to recognise, say, a circle, which is separable in of the circle or out of the circle.
Yeah.
3 layers, yeah, it can give you all kinds
Any
of different.
convex
Yeah.
problem. which is important because this propagation training, when you add layers, it's just becoming slow, really slow. It doesn't make sense basically to us.
But the one good thing about these neural networks is once, as you can see, the structure-wise, yeah, it looks fairly complicated, but once you've got your network, it's not complicated. So you spend time training it, that might be, you know, inefficient, what have you. But once you've got your weights and biases, it's just sort of matrix calculations. You can just literally give it some new input, and very, very quickly you can get a decision. So, because all you're doing is you're just applying 0 and 1 here, calculating this, outcomes the value. So you can take, say, an image of a cat, which is, you know, you can make it grayscale, so you can get pixels 0 to 255. You can turn that into, you can kind of ratio that against like a value from 0 to 1 to feed into your network. And then out comes the other side, you know, value 0 or 1 as to whether or not it's.
So would you have an input layer which has an input per pixel?
You could have an input layer per pixel, yes. So that's how you would say, same with handwriting recognition. You could have like say 50 by 50 pixel input, and you turn that into grayscale, and you use that as your values to feed forward. And then the network can make assumptions about area, shapes, that kind of thing.
You'd have to orient all of them the same way, so you couldn't say turn the cat
Well,
upside down.
if you were
even
to-
if you had in layers.
If you were to give it training data which is always orientated in the same way, then your network generally won't be very good at
Right.
spotting disorientated shapes. So realistically, you want to kind of give it a good training data, a good training data set which includes different orientations, different sizes, different shapes.
Yeah.
So you know, you might want to give it, say, if you're trying to spot the letter A, you might want to give it like that. You might want to give it sort of skew it, all kinds of different shapes, just to give you that kind of that satisfaction that the chances are your network is going to spot, you know, different people's handwriting.
It's trying the training data could almost end up having an autistic network. And you see this in autistic children, is that they can recognise people in a context, but if you change the context, for instance outside the classroom, they can't recognise an individual.
That's exactly right, yeah. So, and that's the danger of overfitting. A good art really with neural networks is try not to give it too much trained data, but give it enough to kind of give you some guarantees that when it comes to generalisation, i.e. you give it new data, it can kind of make good assumptions about that data. So it's kind of a bit of a black art really in terms of the data that you're feeding it in, the learning algorithms you're using, and the optimization that you're doing in order to get better sort of generalization. And there's all kinds of different techniques with neural networks, like there's radio basis function neural networks, which try to give you a more noisier pattern to kind of give you a better generalization. So, for example, if you were to take that straight line, let's forget that it's in two-dimensional space at the moment. A radial basis function might, your data's like this, for example. A radial basis function might give you a line that looks a bit like that, with a little bit of noise, so that it might actually be better at generalisation fitting that data. It's just another technique to use to try and solve finding the optimal decision boundary. So there's lots of research on this. There's lots of different techniques you can use.
How is this better or worse than logistic regression?
Well, it's not a case of whether it's better or worse. It's just you've got this problem to solve. You only know what you know about the training data. You're trying to make an assumption about that training data, so that when you feed it new data, your network's going to be as good as it can possibly be.
Well, I mean, you can use the network, or you can use logistic regression to solve the
Yeah, it's just another technique.
2 layers perceptron is effectively regression, it's solving regression. With some function, like it can be logistic function. So this is it's actually exactly this.
So the black art is choosing.
It's a black art. I think the point I'm trying to make.
Well, the black art, I think it's more with data to not to overfit and to get stuck in local minimum. I think this is where the problems lie.
And what data you use.
So what regards to that local minimum, imagine all the different possibilities of that line separating your data. Let's say that it looks like this. Let's say that the optimal decision boundary is like that. When you're trying to train a network to spot the most optimal, a local minima, or I say I've drawn this wrong way around because it's the maximum, your network will get here and it will converge here because it starts trying to go down this way. It's going to realise, oh man, it's not as good. It's going to come back up and it will consider that to be the most optimal solution, when actually in your space of different lines, that could be considered the most optimal. And there were loads of different techniques for trying to get around that problem as well. But the good thing, this is why the support vector machine uses this large margin classifier, is because it's not susceptible to local minima. It'll always find the most optimal solution based on the training points that you have. So, does that make sense? Or am I going off at a tangent now? So, getting on to the crux of, if you take perceptron, you can't solve a non-linearly separable problem. So how do you solve a non-linearly separable problem with a perceptron? So just 2 inputs, 1 output. Use what it's called here a kernel function or kernel trick. So at the moment your 2D space, your input space here is 2-dimensional. Let's imagine you are actually you want to separate that data. The way you can do it is you can apply a mathematical function to it to transform that into feature space or hyperspace, something that's at a higher dimension. So what you can do, you can apply a function to, say you've got that circle there, that's got an x value and a y value. You apply a mathematical function to both the x and the y to transform it, and that one there might end up here. So you're taking it from a 2-dimensional plane to something that is 5 higher dimensional, and in that space the data may be linearly separable. Does that make sense so far? So the idea being is, instead of just leaving the data as it is, you apply a mathematical kernel function to transform that data. Then you look inside that data to see whether you can now solve that problem using the perceptron, because the data is now linearly separable.
Do functions like that always exist?
There are several functions that are used, and there are several parameters that you can play around with to try and get that data into non-linearly
So it's
separable.
not guaranteed that they exist.
Not necessarily guaranteed, but there are, you can perform good.
Yeah.
You can solve very, very good complex problems by doing this. Like handwriting recognition. You can do that fairly easily.
And does it just have to be a linear function of x and y, or can it be like a more complex function?
It can be a more complex function, but generally with this, in trying to solve a classifier, if you've got 2 classes you're trying to split, you only need that. You only need like x and y. Yeah, it's non-linearly separable, so you might need to apply a mathematical function to separate that. But then once it is separate, you can then use your perception to actually split that data.
Is it implied in the right-hand side that there's more than 2 dimensions? Yeah.
Yeah. There are some really good diagrams out there but realistically you can only draw 3D. So.
Well, I want 5D.
Yeah. Anyone seen the cube or hypercube? That's a good way of thinking. But yeah, so there are several different functions that you can use. There are, and I'll get to in a minute. Yeah, so I'll explain some of the, I'll demonstrate some of the functions in a minute, but if you were to do this, if you were to take your input, which is non-linear separable, apply a kernel function, separate it into this hyperspace, and then you apply your decision boundary and your algorithm for finding the optimal decision boundary, one that separates the data as far as possible, increases the margins between the decision boundary and the data, you can end up with a very, very good classifier. And it's only essentially a perceptron and a kernel function. So instead of having all this complicated hidden layers, you've just got mathematical functions that you apply. So feeding it new information is incredibly quick, and it's a lightweight network, essentially. Does that make sense? And it's in the field at the moment. They, as I said, going back to the background on it, what's made support vector machines very successful is because they can solve problems like digital handwriting recognition without having like complicated network structure, and they perform the same kind of error rate, if you like. They get the same sort of test results as a carefully constructed neural network. So one that's been carefully constructed to actually solve handwriting recognition, which is quite impressive, really, considering you've got just one neuron, you know, a couple of inputs, you apply a quick function to it, you've trained it, you've got your decision boundary, and then you apply that. So I think that's why they have been so successful, really.
I don't think I've properly grasped the difference between the support vector machine and the neural network that created the data points for a training set further points.
Well, a neural network is a more complicated structure. So you've got the first sort of stage of a neural network, which is one neuron, which you call a perceptron. The idea of a support vector machine was to take that neuron and make it better, because when this came around, it could only solve linearly separable data, and the optimization problem on it was just to give you a line that separated. There wasn't any optimal kind of solution to it. So what the difference between that and the support vector machine is the support vector machine tries to make the optimal solution, and it also can solve non-linearly separable data by applying a mathematical function so that you can solve it with just one neuron, as opposed to having to create these complicated networks to give you the lots of different lines separating the data. Does that make sense?
But I don't want to do things.
Okay. So some popular. These are sort of the two really sort of popular like kernel functions that you can use. I've just put them up there to show you sort of like the functions themselves. You just apply them to your x and y, so your two inputs, and that gives you a new value. And then that value is in the feature space, and there's a higher dimension. So if you apply that to all of your, say, your blue squares and red circles, you might find that actually in that space they are linearly separable. And that way you can train your perceptron to find the right decision plane in that space and separate the data. So yeah, you've got this polynomial kernel function and a radial basis function, which are the two sort of popular ones that you can apply. So yeah, that's essentially just going over what I said earlier about the two main aspects of a support vector machine is the kernel function that you apply and the algorithm to solve and find the optimal decision boundary within your feature space. So, if you were to take like the handwriting recognition problem, you've got A to Z, 1 to 9, or 0 to 9, all the different sort of characters that you want to kind of recognise. What we've looked at so far is just two classes that we're trying to separate. So with one neuron, you can't really do, I want to decide whether that's an A, that's a B, that's a C, that's a D. So with support vector machines, what you can do, there's two different sort of arrangements you can look at. You can either have a single perceptron which tells you that is an A against everything else. So you can train that network with, or that neuron with lots of A's, and you give that a 1, and then lots of B's, C's, D's, E's, F, G's, and so forth, and you give that a 0. And then that makes the decision based against A's against every other letter. So you can either do that, or you can have more neurons, which more support vector machines. Each one can be like a separate between an A and a B, an A and a C, an A and a D, an A and an E, and so forth. And then what you can do, you can feed the information through all of those and collect the results, and the majority wins. So if you find, there are more, you can kind of like classify them against each other, so you can say, well, actually it's more likely to be an A because all of the A's versus other letters fire towards an A in that scenario as against anything else. Does that make sense? Mm-hmm. Yeah. So you can kind of, that's another kind of grey area. You can find different different support vector machine network structures to suit the problem you're trying to solve. And there are caveats with that, because obviously if you're trying to get the kind of most efficient and the most sort of accurate, if you're training like A versus every other letter in the alphabet, that's a lot of training data you've got to feed it, and you could be susceptible to overfitting. Also, there's the efficiency in that. It's a lot of data that you require just for one. Whereas maybe you only need the data for the A's and B's, you only need to show a small subset of that data to that one support vector machine. But you end up with lots more neurons to consider. So you have an A versus B, A versus C, A versus D, and so forth. So that's how you apply that to like a digital handwriting recognition problem. You just have lots of support vector machines that classify one from the other, and then you make a majority decision on which one it should be. So why support vector machine? Well, the thing that I like about it is that it's quite an interesting problem to solve. There are lots of tools out there that already do a lot of it for you. There's a really good Java library called SVM, which has all the sort of stuff that you need. So if you want to do this in Java, it's nice and simple and easy. And also it can be considered, it's a lot more modular. So you can choose which kind of kernel functions you want to use. You can play around with the parameters. You can choose what kind of optimization problem you want to introduce. And there's loads more research into how to go about finding a better decision boundary. So the idea being is that you have your neuron, and then you can apply lots of these different techniques to that neuron to make it more efficient and more accurate in classifying the data. So that's what I like about them. And the big sort of like thing is that it doesn't suffer from the local minima problem. So it will always find you the optimal solution given the data that you give it. And that's it. So any more questions?
I'm being a bit dim here, but what is the support vector machine different from perceptron? I know you said mathematically the perceptron can only do separable, whereas support vector machines can have optimal results. But mathematically, what is the function inside the SVM that gives you that additional power? And what training?
If you're considering going from non-linearly separable to linearly separable, that's the kernel function. So think of a support vector machine as an enhancement to a perceptron.
Right.
Because it is just a single, it can be considered as a single neuron which has multiple inputs coming in and one output coming out.
Right.
And that function inside there is what gives you your... And if you weren't to do anything with the input coming in, so if you left it as it is in two-dimensional space, trying to solve a non-linearly separable problem is impossible.
Right.
Because you're only dealing with a straight line in 2D space. Whereas if you apply a kernel function, you're transforming it into a higher dimensional space, and therefore your decision boundary isn't a straight line. It's
And the higher dimensionalness comes from the number of inputs, does it? So if I wanted to transform a 2D into a 3D, then I would have 3 inputs into the X, Y, Z coordinate.
Not so it comes from the inputs, but what you're doing, say for example your zeros, it's a number for saying 1 to 10. That's a 2, that's an 8.
So I was thinking of the letter A.
You might find that a function, for example, to transfer that into a different space, you just have, it's like 2 to the power of 2, 8 to the power of 2.
But I was thinking if I really, but isn't that still within the same 2D space? But if I wanted it, for instance, if I wanted to recognise the letter A and I said, right, all the pixels at A are at Z coordinate 1, and all the pixels that are not part of A are at Z coordinate 0, then I could give it X, Y, and Z and train it. Or is that not the way I would train it?
That's making an assumption about the position on where your character is though, in the pixel space.
Right.
Whereas what I'm saying here is that if you're just using this as a simple example, 8 and 2, your 2 values for going in, say it's like, I don't know, 8 centimetres high, 2 centimetres deep.
Yeah.
If it's non-linearly separable, if you apply just a function of applying to the power of 2, that separates a lot further from there now.
Yeah.
So your data is now shaped a lot differently.
But also Z would be a function of X and Y. If you want to go to higher dimension.
Yeah.
So X is a function of X and Y, Y is a function of X and Y, and so on and so forth.
Okay.
So that there is your kernel function that you apply to your input. And then going into Perceptron, that is now in a space where it can be linearly separable. So Perceptron, if you like, or support vector machine can be trained to separate that and give you the right value out.
Can you think of it as taking your original plane in the two space and imagining it's made of rubber, applying all these transformations?
That's right.
And that's created
But
next.
But what you have to apply, what you apply here, so once you've decided your kernel function, when you feed it new data, you have to make sure it's within the same hyper-dimensional space. So, say you give it new data, say you give it 3 and 7, you have to apply that kernel function. Yeah.
So you would build a network of support vector machines in the way you build a network of Separators.
Yes, but they're not connected, if you like. So you'll build your. So it's not got this complicated network. It's just a long list of perceptrons or support vector machines that tell you, and you feed it into all of them. You feed the same data into all of them, and you decide, well, that's more like an A over a Z. That's more like an A over a B. Well, and if you end up with like all of the A's versus nothing firing, yes, that's an A. That's going to probably sum up, say there's like 26 of them, but firing yes. And the rest of the structure, you might find that actually 26 is the most, and therefore it's more likely to be an A because 26 of those
so you have to
around the A are
a
firing.
function to all the outputs to kind of tally the votes almost.
Yeah, it's tally votes, yeah.
Typical trick.
So from that perspective, yes, you do end up with a long input layer and lots of support vectors to sort of give data, but it's still a lot quicker than, in some cases, than complicated neural net structures. But it's one of those, it's where the sort of side of the fence you sit on really is to what you prefer.
Yeah, well, the complexity and the calculation space with a traditional neural network comes from connections, doesn't it? So if you had an input for each pixel that just did whether it was on or off, and you'd have to have a couple of layers, and you've got full interconnections trained.
Yeah, I mean, with my dissertation I did, there's some training data for digital handwriting recognition, so there was like, I think it was something like 255 by 255 array pixels basically, and grayscale values from 0 to 255 as well, and so that takes a long time to train, but very quick to kind of give you a result back. So, I think it was something like 95% classification, like success as well. So they're quite good. So even someone like me, not the best sort of programmer in the world, can still, you know, develop something to give you quite good results.
So given a set of training data, when you've trained your machines, if you feed it back exactly the same training data, you would expect it to be 100% accurate, or is there the scope for it to still be indeterminate?
No, you'd expect it. With a sport vector machine, you can kind of guarantee that it's going to give you the correct data back, because you have solved the optimal problem separating the two data.
So it's only new data.
It's only new data. Yeah. And that's the whole sort of black art, really. You don't want to underfit, because you're going to get large error problems when you feed it lots of new data. But you don't want to overfit, because then can be considered you're making assumptions about the data that you're training with.
Yeah. That's why you don't use all of your training data as training data. You use it, you take a chunk off. And that's testing data to see what the results, to ensure that the results of your training gave you something reasonable.
Yeah.
So if you had like 1,000 pictures of cats and dogs, say 1,000 pictures of dogs, 1,000 pictures of cats, you might say, I'm going to take 10% of each, train it with those, so 100 dogs, 100 cats, train it with that, and then you test your accuracy of your network based on the 900 of each left. And you'd see what kind of error margins.
So there's no kind of ongoing learning with it.
You can continue to get it to learn. If you want to, you can continue to feed it with
data. Doesn't that
data.
sort of like increase the overfitting?
It does, yeah. So, I mean, I guess if it was one of those things over time, I'd prefer like what they call continuous time neural networks, where you're just constantly feeding the data through time, and it's constantly self-correcting itself over a period of time. So like autonomous agents and that sort of thing, you probably want something like that to kind of, increase sort of like the, efficiency over time. Yeah, if you are interested in the math, there's a really great book called Introduction to Sport Vector Machines, but it's quite heavy on the math, so have a little read.